Okay, now we move on to chapter 3. The second law. In chapter 2, we have learned about the first law of thermodynamics. Now we are moving on to the second law. From the first law of thermodynamics, we learned about energy conservation. Okay? We now know what process, what changes are allowed, what changes to follow the first law of thermodynamics. Delta U is equal to Q plus W. But we do not know the direction of change, especially if the change is spontaneous. There are several changes or processes which occur spontaneously, naturally, as it is, if you just leave it there. And these kind of spontaneous changes do occur with a certain direction. Okay? What direction is determined by this specific change? Is it natural or is it just doomed or whatsoever? Okay? That direction of spontaneous change is related to the dispersion of energy, which we haven't covered yet. And to explain this direction of spontaneous change or dispersion of energy, we need a new concept, new variable called entropy. And based on the concept of entropy, we can explain these behaviors. Okay? Alright. Let's review the first law. First law of thermodynamics. The energy of the universe is constant. Isolated system, for an isolated system, delta U is 0, right? But this first law does not tell us anything about the spontaneity of physical or chemical transformation. For example, let's consider the formation of water, the reaction of hydrogen and oxygen to water. Based on our knowledge up to chapter 2, we know that how to calculate the the standard reaction enthalpy. And if you do that, we get minus 286 kilojoule per mole. Okay? So based on first law, we can calculate delta H or delta U or something like that. Okay? But we don't know if this reaction occurs spontaneously or if the reverse reaction occurs spontaneously. It does not tell us anything. It just tells us about energy or enthalpy change associated with this chemical reaction. That's all, right? But we know that some reactions, and actually not some, most of reactions or changes have spontaneous reaction, such as gases expand spontaneously to fill a container. That's spontaneous change, right? Heat energy moves from hotter object to colder ones. That's spontaneous, right? We know by experience that it occurs spontaneously, right? But those spontaneous processes cannot be determined by delta U or delta H. And that kind of information, we can get it from the second law of thermodynamics. Okay? Let's see some examples why we do not determine the spontaneity of the reaction based on delta U or delta H. Okay. This reaction is exothermic, negative side for standard reaction enthalpy. Okay. And this reaction occurs spontaneously if you supply some amount of activation energy. Okay, then exothermic reaction is spontaneous. There's opposite example. For example, vaporization water. If you have water, liquid state, it vaporizes spontaneously in air, right? And vaporization is endothermic reaction. It absorbs energy. Endothermic reaction is spontaneous. Exothermic reaction is spontaneous. How about mixing gas? If you have two different types of gas, if you mix it, they mix together spontaneously, right? But those mixing does not involve any changes in energy or enthalpy. No change. Exothermic, endothermic, or no change. All of them are spontaneous. Okay? So we do not know, based on first law, what is the spontaneous changes. Okay? What exactly drives this kind of spontaneous changes? We now know that it is not energy or enthalpy, right? Second law of thermodynamics basically gives us clue about this spontaneity of processes, changes. Okay? And there have been many scientists who describe the second law of thermodynamics in different ways to describe the direction of spontaneous change. Some of them are given here. And let's consider only two representative ones, by Clausius and by Lord Kelvin. Okay. To do that, let's first consider a cyclic process. That's here. Okay. From the first law of thermodynamics. Okay. From the first law of thermodynamics, delta U is equal to Q plus W. Okay. For a cycle process. Since an internal energy is a state function, delta U is 0. This result suggests that there could be a certain tool or instrument that runs in a cycle and converts heat into work, which means that since Q plus W is 0, if Q is positive, then W is negative. Okay? So, there is some kind of instrument which absorbs heat from the surroundings while doing a cyclic process, absorbs heat from surroundings and do work on the surroundings. Could be something like this. Okay? There's some instrument which does cyclic process while absorbing heat, giving up work on the surroundings, right? So this kind of instrument is called heat engine. You can imagine an automobile or any kind of engine, right? Basically absorbs heat, converts it into work while running in cycle. Okay? This is heat engine. If you go back to the statement of the second law by Clausius, Clausius said that it is impossible that at the end of a cycle of changes, heat has been transferred from a colder to a hotter body without at the same time converting a certain amount of work into heat. Okay. What Claudius said about the second law of thermodynamics looks like this. There is a cycle, such as heat engine, and it is impossible to transfer heat from a colder body to hotter ones by using this cycle. Okay? This is not possible. This is the statement of the second law of thermodynamics by Claudius. It seems so obvious, right? By experience, we know that energy transfers from hotter to colder body. The opposite is not possible, right? Okay. If you do this, we need some other object doing some work. For example, like representative example of this kind of instrument is what? Refrigerator, air conditioner, something like that. To make the room cold using air conditioner, we need electricity, right? This is the statement of the Claudius, second law of thermodynamics. How about Kelvin? Lord Kelvin said, in a cycle of processes, it is impossible to transfer heat from a heat reservoir and convert it all into work without at the same time transferring a certain amount of heat from a hotter to a colder body. What it means is that, similarly, we have heat engine doing a cyclic process, but it is impossible to get some amount of heat and completely 100% converting it into work. This is not possible. Then what is possible? You need to lose some amount of energy as heat to a cold body. So this is like hot, cold. Let's say QH. Let's see, something like that. This is possible, but converting total heat energy into work without dumping some amount of energy into colder body is not possible. Okay? This is the statement by Lord Kelvin. Actually, both Claudius and Kelvin's statement about the second law of thermodynamics is same. Let me prove it. Just one of them. Okay. Let's see. Let's assume that we have hot body here and cold body here. Okay. Let's assume that there is a heat engine which can convert heat completely into work 100%. We're just assuming, and we are going to show that that assumption is wrong. Okay. we just assume there is a heat engine C which can obtain heat energy from cold body and convert it totally into work 100%. Okay? And let's assume that there is another engine C prime between these two bodies. This is just heat engine. So it observes some amount of heat from cold body as Q2, and also it observes this amount of work as Q1, and simply transferring those two amounts of energy to hotter body. Okay? If you combine these two engines together, those two engines together, what is happening? This engine basically converts this amount of heat Q1 and it gives that amount of energy to this engine. Okay? So within here, there's nothing going on, right? This one just gives this amount of energy, this one receives that amount of energy. That's all, right? So if you combine these two engines, what they do between these two bodies is basically transferring this amount of energy, Q1 plus Q2, to hotter body. Right? And Clausius said this is not possible, right? We started from Kelvin's statement, and it's basically same as Clausius' statement about the second law of thermodynamics, right? Okay. All right. Let's go back. So we learned about the concept of heat engine and the two statements about the second law of thermodynamics. Okay. Now we need to understand what exactly determines the direction of spontaneous change. Okay. Before we do that, when I showed you the statement about Lord Kelvin and Clausius, I showed you hot body and cold body, right? Those hot and cold bodies are examples of heat reservoir. Heat reservoir here. Heat reservoir. Heat reservoir is just an ideal concept, which is a very large system of uniform temperature, constant temperature, which does not change regardless of the amount of heat added or withdrawn. As I showed, this heat reservoir gives or receives energy, heat energy, between these engines, right? Engine and reservoir. But we assume that these two reservoirs, hot or cold ones, are really large. So even though some amount of energies are transferred in between, okay, their temperatures do not change. That's the assumption for the definition of heat reservoir. Okay. All right. Now let's move on. What exactly determines the spontaneous process? What's the direction of spontaneous process? Let's consider two different cases. Very brief examples. If you drop a ball elastic ball in a vacuum. If you just drop it, at the beginning it has potential energy, and as it to the collision on the ground, all the potential energy converts into the kinetic energy and goes back, right? Kinetic energy decreases, potential energy increases, something like that. This shows the first law of thermodynamics, right? Energy is conserved. But what if we drop an egg from a certain height? Egg does not bounce back. It just boom, right? Why? Initial and final states are same. Energy is conserved. Initial and final states are not the same. Right? It has some energy, potential energy, but now, where is the energy? Energy should be conserved, according to the first law of thermodynamics, right? Energy is gone to some kind of energy. It is converted, mostly as heat on the ground, molecules comprising the ground, right? Also to the egg, right? Form of energy has been converted into heat. And this potential energy is, if you recall the formal definition of work and heat, remember from chapter 2 that work is a form of energy associated with organized motion of molecules, right? On the other hand, heat is an energy associated with random, disorganized motion of energy molecules, right? Potential energy has organized motion, right? Heat, random motion. Organized motion has been changed to random motion of molecules. Okay? One example. Similarly, if you drop a ball not in a vacuum at the atmosphere, it will bounce back, but it does not reach to the original height. Bounce back, and finally it stops, right? The reason why it stops bouncing, is that as it collides with the ground, it loses some amount of energy as heat to the molecules on the ground, to the molecules on the ball, right? Finally, it stops and rests. Right? Organized motion change, converts spontaneously to disorganized or random motions of molecules, right? Okay. Is the opposite process possible? Let's say that we put the ball on the floor and we heat it. We just add heat, random motion. We add heat. Would the ball just bounce up spontaneously? That's not possible, right? That's impossible. This process is possible, spontaneous, but ball resting on the ground bounce up by just hitting them. It's not possible, right? Now you can see the difference, right? What is the direction of spontaneous change? Okay? Spontaneous change is associated with dispersal of energy. Energy is dispersed as random motion of molecules. Okay? That determines the direction of spontaneous change. Okay? So this is the second law. First law of thermodynamics only shows us which process is possible, permissible, in terms of the equation delta U is equal to Q plus W. Second law of thermodynamics shows us that which change is spontaneous, which one is not. This process is spontaneous, but this process is not. Okay? Interesting. So, as a result, the whole universe tends towards more random, disorganized states, spontaneously. That's the fate of us, right? It's very melodramatic, right? In the end, the whole universe would be gone, right? Because all the energy would be converted into random, disorganized motion as heat, right? Although we are living in an organized motion by using organized energy, right? In the end. Right? Okay. So this second law of thermodynamics, and to quantify this random or disorganized states, to quantify the disorder or randomized motion, we need another function, another state function, which is called entropy. So entropy basically represents the degree of disorder or degree of random motion. Okay. All right. We can just read this slide. Before we move on, let's review what is spontaneous process. Spontaneous is something that occurs naturally, right? Which means that it's the same as irreversible way. Spontaneous change is same as irreversible change. Okay? And remember that we introduced an ideal concept called reversible change, right? Reversible change is not spontaneous. Okay? And all the processes that we can experience is irreversible or spontaneous change. Basically, these two are same words. All right. So we introduced new state function called entropy to describe the degree of random or disorganized motion. And entropy is denoted as large capital S. Okay. Okay. If you review, first law says that internal energy is conserved for an isolated system. Second law basically shows us what changes are spontaneous. Okay? And we saw that during irreversible or spontaneous changes, all the energies converts into more random, more disorganized states, which means that entropy always increases in the course of spontaneous change. Total entropy always increases. Okay? For an isolated system. So, since this is total entropy change, total means system plus surrounding. Okay? Remember? Okay? So total entropy always increases, and total entropy consists of system entropy and surrounding entropy. Alright, so now we know what entropy is and what spontaneous changes are. Okay, now we need to define entropy thermodynamically. Okay, the thermodynamic definition of entropy is follows. ES is defined as TQ reversible over T. So small change in entropy ds is defined as dq heat for reversible process divided by temperature. Okay. This is just the definition of entropy. Then we can see why entropy has this form. Because entropy is related to random disorganized motion, which corresponds to heat, right? Heat. Okay? Why reversible? Because heat is path functions right? So it depends on path. So to define something, we need some reference point, okay? Some standard. So we use reversible process as reference point. Then why T in the denominator? Because if the same amount heat is supplied, if the temperature is low, then the change in the degree of disorganization or random motion will be larger, right? That's why the definition of entropy looks like this. So from the definition of entropy, if you want to calculate the measurable change of entropy delta S, you can simply integrate this over initial to final state. Okay? So what you need to do, if you want to calculate an entropy between two different states, you first need to find the reversal path, because the definition is reversible, and you calculate the amount of heat and divide it by temperature and you integrate it. Okay? That's all. Let's do an example. Oops, sorry. Calculate the entropy change for an isothermal expansion. Isothermal reversible expansion of a perfect gas. Okay, remember from chapter 2, right? Since this is ideal gas, delta U is 0 if the process is isothermal, right? So Q plus W is equal to 0. Okay? What we want to calculate is delta S. You can do this integration. dq reversal over T integral, right? Since this process is isothermal, temperature is constant, right? So if you move temperature out of the integral, you can get this, right? That's all. And for reversible isothermal expansion, Q reversible is nRT log Vf over Vi, remember? So delta S corresponds to nR log Vf over Vi. Okay. So if Vf is larger than Vi, if the gas do the expansion, which means that delta S is positive. Alright. Oh, one thing I forgot to mention is that the definition of entropy, if nothing is given as subscript of entropy, which means the entropy of system. Okay? You need to remember this. Although nothing is given here, this means that this one is for system. You can do the same expression for entropy for surroundings, but for surroundings, it's a bit more easier to calculate the entropy change. Remember that total entropy change is entropy change of system plus total entropy change of surroundings. So if you want to check that this is really true, you need to calculate this. You need to calculate this, and you sum up and check if this is really positive. Okay, that's really not really easy, right? Takes time. But for surroundings, it's a bit easier to calculate the entropy change compared to system, because surroundings are treated as really large one compared to system, right? So we can consider them to be isothermal and at constant pressure. Compared to system, surroundings are really large, right? Surroundings are something that are not system, right? So although there is something going on between system and surrounding, they do work, they transfer heat, etc. we can assume that surroundings do not change temperature and they maintain constant temperature, constant pressure. Okay? In that case, if the temperature is same and pressure is same for the surroundings, heat of the surroundings should be same as delta H, at constant pressure, right? As you have learned from chapter 2. And enthalpy is state function, okay? Right? So, by definition, ds surrounding is equal to dq surrounding reversible divided by T surrounding, right? This is the definition of entropy. But since surroundings are so large, it can be assumed to have same temperature, constant temperature and constant pressure. The heat is same as delta H, which is state function. So this dq reversible doesn't need to be reversible, right? It could be just dq, right? Because it is state function. Okay. So simply delta S surrounding can be calculated as integral of this, but T is constant, right? Isothermal. So we can get this very simple expression for the entropy change of surroundings. Okay? So if the process is adiabatic, if there is no heat transfer between system and surroundings, then Q is 0. Then delta S surrounding is 0. Very simple, right? Okay? So we need to use the same expression for the calculation of entropy for system and surroundings, but for surroundings, it gets much easier to calculate it because surroundings are considered really large one. Okay? Alright. Entropy as a state function. When we introduced the second law of thermodynamics, we said that we need new physical variable called entropy, and that is a state function. We need to show that that is really true, that entropy is a really state function. So let's prove that. To prove that entropy is a state function, the integral of the S must be independent of path, which means that if you integrate the definition of entropy ds over a cyclic process should be 0. Okay? If you can show this is true, then entropy is a state function. Okay? We'll demonstrate this, and we'll follow these 3 steps. First, we'll show this is true for a special cycle, which is called Carnot cycle, especially for perfect gas. So we'll first show that this is true for a very specific case, special cycle, special gas. And secondly, we'll show that this is true for any substance, not perfect gas. Okay? And finally, we'll show that this is true for any cycle, not special cycle. So we'll generalize it, and we'll show that this is true all the time, which means that entropy is a state function. Okay, as we have introduced before, we'll demonstrate that a physical variable, entropy, which represents the disorderedness or the randomness of the system, this which is a state function. So we'll demonstrate that the entropy is a state function. So as I mentioned, that we'll follow these 3 steps to demonstrate it. First, we will demonstrate that this integration over closed loop a special cycle, for a special system, which is perfect gas, is true. And then we'll demonstrate that this is true for any substance, not only perfect gas. Also, we'll demonstrate that it's true for any cycle, not just Carnot cycle. Okay? So let's do the first step. Okay. First, we need to introduce what the Carnot cycle is. Carnot cycle, named after Sadi Carnot, has 4 reversible stages. So, Carnot cycle is also called Carnot engine. You remember what heat engine is, right? Heat engine is a tool used to convert heat to work by doing cyclic process, right? It's the kind of heat engine, Carnot engine. Okay, so it does this kind of cycle. Start from A, B, C, D, A, something like that. It does this again and again, this cycle. Okay, by doing this cycle, this Carnot engine converts heat. It absorbs a certain amount of heat from hot reservoir and converts it to work. Okay, and this Carnot cycle have specific 4 stages: A, B, B, C, C, D, D, A. All of these 4 processes are reversible. Okay, first properties, first characteristics are they are reversible, and 2 of them are isothermal, and the other 2 are adiabatic. Okay, so first A to B, process number 1 is isothermal reversible expansion, right? It shows the PV, pressure as a function of volume diagram, right? So from A to B is expansion, and it is reversible and isothermal expansion. Okay, B to C, also expansion, right? Volume increased. And BC process is reversible expansion, a diabatic reversible expansion. Okay? And from C to D, which is compression, right? Volume decreased, right? But compression, reversible isothermal compression. Okay? D to A, also compression, reversible or diabatic compression. So basically, Carnot cycle or Carnot engine consists of 4 processes, okay, which are reversible processes. 2 of them are isothermal, and the other 2 are diabatic. Okay. What we want to calculate is that for this Carnot cycle, this is 0. We want to demonstrate this. Okay. So let's calculate entropy change during this Carnot cycle for perfect gas. Okay. All right. First, we separately need to calculate entropy change each of these for each of these process 1, 2, 3, and 4. One thing which is good is that these 2, number 2 and number 4, are a diabatic process. A diabatic, which means a diabatic Q is equal to 0, right? For a diabatic process, a diabatic expansion, a diabatic compression. For both of them, Q is 0, which means that delta S is 0. So we don't need to care about these 2 processes for the calculation of entropy change. Okay? All we need to calculate is entropy change during this process and this process, 2 of isothermal expansion and compression processes. Okay. So during the first process, reversible isothermal expansion from A to B. Okay? We say that this isothermal process occurs at temperature TH. Okay? Then delta S should be equal to QH over TH. Here, QH is the heat supplied to the system, to the engine from a hot reservoir. Okay? Right? Since this is isothermal reversible expansion, you remember that for a perfect gas, for isothermal process, delta T is 0, which means that delta U is 0, and delta U is equal to Q plus W. Okay? And during this expansion, the system, the engine, does work on the surroundings, right? So W is negative, which means that Q is positive, right? This amount of heat is absorbed by this Carnot engine. Okay? So delta S for first isothermal expansion is QH over TH. Okay? Similarly, delta S during isothermal compression should be like this, right? QC is the amount of heat released from the system, from the engine to the surroundings, and TC is the temperature during this isothermal compression process. In this case, QC should be negative, right? The amount of Q should be released from the engine to the surroundings. Okay. Alright, it's done. So the overall entropy change during this Carnot cycle or Carnot engine should be sum of these two. Okay? QH over TH plus QC over TC. Right? Simple. And we'll show that this is 0. Okay, let's show. Let's demonstrate this. It's actually very easy. If you recall chapter 2, for reversible isothermal expansion of perfect gas, you remember? Q was represented as nRT log V over V, right? Remember? Okay. So QH during isothermal reversible expansion should be nRTH times log VB over VA, final volume to initial volume. Okay. Similarly, for isothermal reversible compression, QC should be nRTC log VD over VC, final volume, initial volume. Okay, we got two expressions for QH and QC. Also, we have learned from chapter 2 that for reversible adiabatic processes, remember we had this kind of relation, right? When we calculated the final temperature during adiabatic expansion, we got these kind of expressions, right? We have TF over C equals VI TI over C. Here C was C molar heat capacity constant volume over gas constant, right? So for reversible adiabatic processes, BC and DA, two of these processes, this relation should hold, right? These two, right? BC, DA. These two processes, these two expansion processes are adiabatic, right? So we have these two expressions too, okay? These two equations. Alright. If you multiply by these two equations together, left side together, right side together, then you get this expression, right? You just multiply this by this by this, okay? Then you get this. You can simplify by removing these two, okay? Then you get this, okay? VA over VB is equal to VD over VC. You can put this to here, right? Okay. Okay. Then you can simply rearrange and you can simply show that this is 0. It's quite simple. Okay. You can do the final calculation by yourself. Okay. So we got the first demonstration that entropy is a state function for special cycle, Carnot cycle for special substance, perfect gas, right? For perfect gas, for Carnot cycle, delta S is 0 for cyclic process, which means that entropy is a state function. Alright, now to the second step. Now, for the second step, we want to show that entropy is a state function. So delta S is 0 for cyclic process for any substance, not just perfect gas. Okay? Right. To show that, to demonstrate that, we first need to introduce a new concept called efficiency of heat engine. Okay, let's use the whiteboard for a while. Oops, sorry. Okay. Alright. So Carnot engine, we show that is a kind of heat engine. So it could be represented something like this. Engine does cyclic process. Okay. It observes a certain amount of heat, QH, from hot reservoir. Okay. And it converts heat to work. Okay. And some amount of heat should be discarded to the cold reservoir. Right? This was the second law of thermodynamics. Remember? Okay. Okay. So since this is engine, we define the efficiency or denoted as epsilon of a heat engine as work performed over heat absorbed. Okay, so there could be various types of heat engines. Okay, and what heat engine does is basically convert heat into work. Okay, a certain kind of heat engine could much more work from heat compared to other engines. Okay, that's why we define efficiency of heat engine as this. How much work does this engine does as a function of amount of heat it absorbed. Okay, if you recall the sign convention of heat and work for a heat engine, everything is based on the system, heat engine, if it gains energy or not. Okay, so heat is observed, QH is observed by system, so QH is positive, right? W, this engine does work on the surroundings, right? So W is negative. Some amount of heat is discarded from the engine to the cold reservoir, so QC is negative. So sometimes this sign convention is a bit confusing. So to make things clear, it's usually easy to use these absolute numbers for for the calculation of efficiency of heat engine. Okay, so here W, absolute number of W, could be represented as QH minus QC easily, right? Easy? Okay, so which is 1 minus QH QC. Okay? And as you remember from previous slide, for the calculation of Carnot engine, for Carnot engine, it is same as T minus 1 minus TC over TH. Interesting, right? The result is very interesting. Efficiency of a heat engine, no matter what the engines are, no matter what the substances are, only depends on the temperatures of hot reservoir and cold reservoir. That's the conclusion of this second demonstration. Okay? We wanted to demonstrate that for any substance, entropy is a state function. Okay? For any type of engine, and efficiency of heat engine, which is defined something like this, is same as this. It only depends on the temperatures of hot and cold reservoir, not the engine. So we'll show that if this is really true. Alright. Okay. Let's show that. So let's do like this. Alright. So we have hot reservoir and cold reservoir. Okay. Let's say that we have Carnot engine between these two reservoirs. Okay. So Carnot engine work like this. Okay. So it absorbs this amount of heat QH and converts it to work, and the rest of the heat, which should be QH minus W, should be discarded to cold reservoir, right? Okay. And let's assume that there is another engine called E, which is also a reversible engine, but not the substance of perfect gas. This is just a reversible engine between these two reservoirs. Okay, we just assume it. We assume that it also absorbs some amount of heat, QH prime, and we assume that this engine also does work this amount, W, and discard this amount of heat to cold reservoir. Okay? One thing to note is that both engines are reversible engines. Okay? If you recall the definition of reversible process is a process in which the whole process is basically occurs very close to equilibrium, and we can easily change the direction of processes, right? So we can easily change the direction of processes. So let's say that we run the Carnot cycle backwards. Okay? Carnot cycle was something like this. Okay? From A to B, B to C, C to something like this. Okay? this was Carnot cycle, right? So we run it backwards to this direction. It is easy because Carnot cycle is a reversible cycle. Okay? So we run the Carnot cycle backwards like this. Okay? We can run it backwards. We can run the engine backwards like this. Okay? And we assume that the efficiency of engine E is larger than the efficiency of Carnot cycle. We just assume it. Okay? And we'll show that this could be not the case. Okay? So by showing that the original assumption is wrong, we'll demonstrate that the efficiency of any kind of reversible engines between the same hot and cold reservoir have same efficiencies. So we'll basically what we'll do is that we assume this and we'll demonstrate that this assumption is wrong. So we'll finally show that this is same for any reversible engines between the same hot and cold reservoir. Alright. So efficiencies are same. The efficiency of engine E are larger than the efficiency of Carnot cycle. Okay. Then we can show this efficiency as W over QH prime. Okay. W over QH. Okay. Since we have same W, which means that QH is larger than QH prime. Okay. And we could run the Carnot cycle backwards. Okay. And interesting is this engine E does this amount of work. And to run the Carnot cycle backwards, we need same amount of work. Interesting, right? Then we can just simply use this work to run the Carnot cycle backwards. Okay? Same amount of work, right? Alright. So we run both engines together, right? By using this amount of work generated by this engine, use this amount of work to run this Carnot cycle backwards. Okay? So if you combine these two engines together, we can calculate net amount of heat flow between hot and cold reservoir. Okay? So there is hot reservoir, cold reservoir, two engines together, E and C. This engine generates this amount of work. This engine uses this amount of work. So work is basically removed, right? Okay. What these two engines do, okay, is that let's say like this. We just calculate net heat flow from cold reservoir to engine. That would be QH minus W, okay, minus QH prime minus W, right? So basically what we want to calculate is net heat flow from here to here, okay? So this is QH minus QH prime, right? And we can also calculate the net heat flow from engines to hot reservoir. QH minus QH prime, same. And since QH is larger than QH prime, this is positive. Okay? So we combined two engines together. And what these engines do is basically flow this amount of heat from cold reservoir to hot reservoir. Okay? This is wrong, right? According to the second law of thermodynamics by Clausius, right? So, the original assumption is wrong. We can show that the opposite is also same, right? So, as a result, basically, what we found is that all reversible engines between same hot and cold reservoirs have same efficiency, which means that no matter what the substances are, it doesn't need to be perfect gas. No matter what the substances are, engines are basically same. Or entropy is a state function. Okay? Alright. So this is the second step to demonstrate that entropy is a state function. Okay. And the final step is that we'll show that entropy is a state function no matter what the cycles are. Any cycle. Any cycle, for any cycle, entropy is a state function. So let's assume that we have a certain cycle, something like this, any cycle. Okay. And let's assume that, let's just assume that we can easily put the isotherms and adiabats, very small ones, like this. Isotherms, many different isotherms at different temperatures. Okay? Also many adiabats. Okay? Okay? Right? And each of these small cycle, each of these small one, isotherm, adiabat, isotherm, adiabat, which is Carnot cycle, right? Okay? So, let's say that we add up whole entropy change of each of these small cycles, all of them, inside of this arbitrary cycle. Just basically add up all of these Q reversal over T for each of these small cycles. Okay? Then what happens is that you have this cycle and you have another cycle like this. Okay? And when these two cycles meet together, okay, the direction of the integration here for blue one, the direction is from left to right. Okay? For red one, the direction is from right to left. Okay? So it automatically cancels out. We don't really need to calculate it. Okay? It happens for all of these small Carnot cycles when they meet together. All of them, right? All of them inside of these small cycles, right? Except the perimeters. Except along the perimeter. So this should be same as Q reversible over T for perimeter. Okay? And if you draw these isotherms and adiabats with very small gaps, the whole perimeter should correspond to this original arbitrary cycle. Okay? So, which means that T over Q is 0 for any cycle, not just for Carnot cycle. Because any cycle, any reversible cycle can be considered of many small Carnot cycles. Okay? So finally, we demonstrated that the entropy is a state function using these 3 steps. All right. Okay, let's go back to the slide. Clausius inequality. Clausius inequality is something, it's basically a mathematical explanation of the second law of thermodynamics. So basically it shows that the definition of entropy is consistent with the second law of thermodynamics, which means that the total entropy change for spontaneous or irreversible changes are positive, always positive. So we show that. Okay. Alright. So let's see an example. Isothermal expansion of a perfect gas. So we encountered this many times, right? Now you are familiar with this. Okay. Okay, isothermal expansion of a perfect gas. So let's consider 2 different cases. Isothermal expansion for reversible process, isothermal for irreversible process. Okay. All right. So the amount of work for the isothermal reversible expansion was something like this. Remember, minus nRT log Vf over Vi. Okay. For irreversible isothermal expansion, if the external pressure is same as the final pressure, okay, then it should be minus Pf delta V, right? Okay. So since this is perfect gas, P should be equal to nRT over V, right? So it can be represented as this equation. Okay. Let's say that the final volume is twice as the initial volume, 2 Vi. Then you can easily calculate that the amount of work for both reversible and irreversible processes like this. Okay. And you can easily see that more work is done on surroundings by reversible expansion, minus 0.63 compared to minus 0.5. Okay. All right. So let's calculate delta S. Okay. Since we want to show that this is really truthful, this is really follows the second law of thermodynamics. So let's first calculate delta S for the system, for the piston. Delta S from the definition is Q reversible over T, right? Since this is isothermal process, we can use this expression. So for both processes, reversible or irreversible processes, delta S system is same as this, because this is the definition of delta S system. Okay? But delta S surroundings are different. Okay? Because for the calculation of delta S, entropy change for the surroundings, remember, all we need to know is the amount of heat and the temperature, right? So for reversible expansion, delta S surroundings should be minus 0.63 and all, because this amount of heat is transferred from the surroundings to the system. Okay? On the other hand, delta S irreversible process for the surroundings are minus 0.5 and all. Okay. So if you add up these two values, you get delta S total by summing up the system and surroundings. Okay. For reversible process, delta S total is 0. There is no entropy change for reversible process. Okay. Reversible process is ideal process. Okay. And the second law of thermodynamics shows that delta S is positive for irreversible process. Okay. For irreversible expansion, delta S total is plus 0.193 nR, plus positive. Okay. Reversible processes, total entropy change is positive, always greater than 0. Okay. Alright. Similarly, we can get similar expressions, which is called Clausius inequality, as shown in this box. Okay. This is actually very simple. Let's use the whiteboard. Just a sec. Okay. Clausius inequality, which is represented as ds system is always larger or equal to dq over t. What this means? Okay. Let's compare the reversible and irreversible processes. Okay. If you compare the amount of work done during reversible process and the amount of work done by irreversible process, if you just compare the absolute amount, during reversible process, the system does more work, right? So this amount should be larger. Okay. If the work is done by the system on the surroundings, then the sign of W is negative, so we can remove this absolute sign. Minus dW reversible is larger than minus dW. Okay. If you move minus dW to the left side, then you get dW minus dW reversible is larger or equal to 0. Okay. Okay. From the first law of thermodynamics, du is equal to dq plus dw. Okay. This first law should also hold for reversible process, for any process actually. This is the law. Okay. Since dw is larger than dw reversible, dW, this one is larger than this, which means that the Q reversible is larger than the Q. If you divide both sides by T, this is a definition of entropy, right? So entropy change for the system is always larger than the Q over T for any process, any irreversible processes. Okay, this is called Clausius inequality. The importance of this Clausius inequality is that it shows basically shows the consistency between the mathematical expression and the second law of thermodynamics. For example, let's say that the system is isolated, or isolated system. For isolated system, Q is 0, right? Which means that is always positive. The entropy of system never decreases. This is the second law of thermodynamics, right? So this is basically same expression for the second law of thermodynamics. We can see the similar examples shown here. Okay. Similar examples of the second law of thermodynamics. For example, example number 1, irreversible adiabatic change. That's obvious. For adiabatic change, dq is 0, so ds is always positive. Okay. Alright. Irreversible isothermal expansion of perfect gas. If into a vacuum, if the expansion is free expansion, then W is 0, Q is 0. So this is true from the Coulombius inequality, which means that the S total is positive always. Okay. Second law of thermodynamics. Second law of thermodynamics. Okay. How about spontaneous cooling? Let's say that we have hot reservoir, cold reservoir. By experience, we all know that some amount of heat would spontaneously transferred from hot reservoir to cold reservoir, from hot temperature to cold temperature. The flow of heat is spontaneous, right? Let's calculate the entropy change from this process. Okay, so hot reservoir lost this amount of heat, dq. Okay. So the entropy change for the hot reservoir should be minus dq over th, right? It lost this amount of heat, so entropy is decreased for hot reservoir. How about cold reservoir? It gained this amount of heat, dq. So entropy change should be plus dq over tc. Okay. So if you want to calculate the whole entropy change for both of these reservoirs, should be like this, right? Which is this. If th is larger than tc, since this is hotter than cold reservoir, then the S is positive. So this kind of spontaneous heat transfer from hot to cold ones are spontaneous, irreversible. It's obvious. Alright, this is the end of section 3.2. Alright, let's move on to the section 3.3. Entropy changes and processes. In this section, we'll calculate the entropy change for various specific processes. We learned what entropies are, the definition, the mathematical definitions basically. So we now are able to calculate the entropy change. So we'll basically calculate entropy change for various processes, such as physical changes such as phase transition, expansion of perfect gas. We already have done it a few times, right? Variation of entropy with temperature. Like that. Alright, let's do it. First, the most familiar one, expansion of a perfect gas. We already have done it, right? Delta S for isothermally expanding perfect gas. Okay, for isothermal expansion. Okay, delta S was an R natural log Vf over Vi. Okay. Alright. So this delta S is for the system, right? I mentioned, remember, that if there is nothing here, it represents system. Okay. We calculate this for reversible expansion, right? Remember? But this equation applies for both reversible or irreversible processes, because entropy for the system is a state function. Okay? It should be same no matter what the processes are. Okay? Alright. But total entropy change would be different depending on the processes, right? This is entropy change for the system. Okay? You have to remember it. Okay? You have to differentiate between system, surroundings, and total change of entropy. Okay? So let's calculate the total entropy change for reversible and irreversible expansion. For reversible expansion, delta S surrounding should be minus delta S. Same amount of heat, okay, at the same temperature. So the total change of entropy should be 0 for reversible process. Okay, we already have seen this when we dealt with the Clausius inequality, right? How about for irreversible expansion, especially free expansion? If the expansion is free, expansion basically to the vacuum, W is 0. Since this is isothermal expansion, delta U is 0 for perfect gas. So Q is also 0 from the first law of thermodynamics. Since Q is 0, delta S surrounding is 0. Okay. So delta S total should be same as delta S system, which is this, which is positive, right? For irreversible, spontaneous process, delta S total is positive. Entropy change at a phase transition for a physical transformation. Okay. When phase transition occur, such as melting, boiling, sublimation, something like that, external pressure is constant. External pressure is constant. Okay. Which means that the process, the phase transition, occurs as a reversible process because it maintains mechanical equilibrium. Okay? So, during this phase transition, at constant temperature, at constant pressure, heat transfer between system and surroundings is reversible since two phases are in equilibrium. Same pressure, same temperature. Okay? Easy, right? Reversible process. Alright. So, at constant pressure, the amount of heat is same as enthalpy change. Okay? So, entropy change during phase transition should be Q over T, but Q is same as delta H, so delta H over T. So for example, if you want to calculate the entropy change during melting, you can simply put the enthalpy change during melting divided by melting temperature. So easy, right? Okay? So if you compare different types of phase transition, for example, melting or boiling, both of them are endothermic process. Okay? So Q is positive, which means that delta H is positive, which means that delta S is also positive. Entropy increases when melting or boiling occur, right? That's obvious, right? Because this orderness increases. On the other hand, for exothermic process, such as freezing and condensing, Q is negative, delta H is negative, so delta S is also negative. Entropy decreases when exothermic phase transition occur. For phase transition, there's an interesting empirical rule called Troughton's rule. Troughton's rule basically states that when you compare the entropy change for vaporization for various materials, they have very similar numbers. Okay? When you compare the standard entropy of vaporization for different materials, it has very similar number, right? It's interesting, right? The reason why is that entropy change is associated with disorderliness during this vaporization from liquid to gas. So it should be related to the volume change during vaporization from liquid to gas, right? The fact that the molar entropy of vaporizations are similar for various types of materials is that the volume change is very similar from when they vaporize from liquid to gas. Okay? There are exceptions actually. For methane and water, they have somewhat different standard entropy of vaporization. Methane has a bit smaller entropy change when they vaporize. On the other hand, water has a bit larger entropy change when they vaporize. The reason why is that in water, molecules are more organized in the liquid phase because of hydrogen bonding. In liquid phase, water molecules, H2O, have large number of hydrogen bonding. So they are quite ordered compared to other materials. So since they are more ordered in liquid phase, which means that in liquid phase the entropy of H2O is smaller than other materials. So when water molecules vaporize, they basically experience more change of this order. Okay? So the change of entropy is larger than other materials. Okay? On the other hand, for methane, okay, entropy of gas is slightly lower than other materials. If you compare the chemical structures, benzene, tetrachlorocarbon, cyclohexane, hydrogen sulfide, methane is very simple one, CH4. They are totally symmetric, right? So this entropy of methane is relatively smaller than other materials because of those symmetric structure. Okay? So associated disorder in the gas phase is lower than other materials. That's why entropy change during vaporization is smaller than other materials. Variation of entropy with temperature. We can calculate the entropy change at a specified temperature, right? What if temperature changes? Can you calculate the entropy change as a function of temperature? The answer is yes. Okay. How? This is the basically definition of entropy change, right? Delta S is integral dq reversible over T. Okay. We assume that the system is subjected to constant pressure. The process is constant pressure process. Then the Q reversible should be equal to Cp dt. Okay? Right? Something's not correctly written. Actually, if the system is not doing expansion work, that's not true actually. If the system is not doing non-expansion work, we are basically ignoring non-expansion, other types of work. Okay. Anyhow, the Q reversible should be equal to Cp dt when the process is at constant pressure. Okay. So we put this expression here we got this, right? We basically can calculate the entropy change as a function of temperature if you have information about heat capacity at constant pressure. Very simple, right? If heat capacity is constant over temperature range, we can simply use this expression to calculate entropy change as a function of temperature. Similarly, let's move on actually before we do this. Similarly, if the process is at constant volume, then we can simply replace this dq reversible with the v dt. Okay. If the pressure is constant, Cp dt. If it is isothermal expansion, we can use this expression to calculate entropy change. So, depending on the situation, we can easily calculate entropy change as a function of a certain physical variable. Okay. What if any of these two variables change at the same time? What if? What if both T and P or T and V change? How can you calculate entropy change? Actually, it's very simple. Let's go back to this example. How can you calculate delta S when argon at 25 degrees C and 1 atm in a container of volume 500 cubic centimeter expands to 1000 cubic centimeter and is simultaneously heated to 100 degrees C? Okay? Volume changed from 500 to 1000, temperature changed 25 to 100 degrees. Both variables changed at the same time. We learned how to calculate entropy change as a function of specific variable, pressure, volume, or temperature. But both variables, temperature and volume, change together. How can you calculate this? It's actually very simple, because as we have demonstrated, entropy is a state function. We don't really need to follow the specific path to calculate this. We can detour. We can use different paths to calculate it. How? We can separate this process into two different processes. First, isothermal expansion to final volume. We first fix the temperature as 25 degrees C, and we change volume from 500 to 1000. And then we fix the volume as 1000 cubic centimeter. We increase the temperature from 25 to 100 degrees C. Simple, right? So we separately calculate each of these and we combine them. So first, we calculate the entropy change during expansion from 500 to 1000 cubic centimeter. Easy, right? We calculate the entropy change at constant volume from 25 to 100 degrees C. That's also easy. We just combine these two. That's the entropy change for this problem. Okay. All right. I'll skip this part. Okay, just read it. Okay. Final slide. Measurement of entropy. So now we know how to calculate entropy as a function of temperature. Okay. So what if we want to define entropy S at a specific temperature T? If you want to define T at a specific temperature, okay? This should be very easy, right? First, we need to know the value of entropy at absolute zero temperature, 0 Kelvin, S0, okay? And then, from 0 Kelvin to melting temperature, the material is solid right? So if you have information about heat capacity at constant pressure for solid, you can use this integration to calculate the entropy change from 0 to melting temperature. Then, at this temperature, Tf, melting occurs, right? During phase transition, we can calculate the entropy change if you have information about the enthalpy change during melting, right? Melting temperature. Okay? From melting to boiling, the material is liquid, right? So if you have information about the heat capacity at constant pressure for liquid, you can use this integration to calculate entropy change, okay? And at boiling temperature, boiling occurs, phase transition. So we can calculate entropy change if we know the enthalpy change of vaporization, boiling temperature. And above boiling temperature, the material is gas. So if you have information about the capacity of gas, then we can calculate it. Okay? All these properties we can get the information easily, right? Easy, right? You can read this part. So, alright. So, heat capacity, enthalpy, melting temperature, boiling temperature, all informations we can easily get. The problem is, we don't know what this is. Entropy at absolute temperature 0 Kelvin. Okay? If we can define this, we can easily calculate or define the entropy at specific temperature T. Okay? So definition of this is related to the third law of thermodynamics, which will be covered in the next section 3.4. Okay, so this is the end of 3.3.